In our last video, we were looking at inverse functions. And when we first learned this in college algebra, the companion to inverse functions is composite functions. Do you remember we would write f of g like this, or we could say f of g of x. And so what this means, the way I teach this, is that this creates an assembly line. I like this notation better, but you'll see both. And here's what it means. If we have these two machines, they are put on one single assembly line. And so what happens here is I have some value of x that's going to go into the first machine. And if you remember, this notation means the g of x is first. The inside machine, or the second one if you're using this notation, this is the first machine in the assembly line. X goes in to the function g of x. Now g of x does something to that function and it comes out the other side. And then it instantly rolls right into the second one. It goes right in, whatever you got for g of x, the value that came out of that machine instantly rolls into f of x and then comes out the other side. That is the idea of a composite function. So again, that's a quick review here, but we're going to do that now with compositions that involve the inverse function. So we're going to make these same machines, but now with trig functions. Now, there's a lot going on here, but there's going to be two types of problems. We're going to see problems where what starts on the inside is the inverse. And we're going to see problems with where what starts on the outside, or what starts first on the assembly line, is just the good old sine function. So it matters. Like what we're going to do here is going to depend on which one goes first. Okay, now a quick word. What we're going to do is not terribly difficult, but it's just becoming confusing. Like there's just so many ideas that this starts to become a little bit overwhelming. So I'm going to talk you through it the best I can, but it's repetition here that I think will help you wrap your head around what you're supposed to do in this situation and what you're supposed to do in this one. So the first one here, we're going to look at the most basic idea, is this. Look at A here. I've got a function, or an assembly line, because I have a composite. So I'm going to put pi over 3. Remember, what's on the inside is the first machine. So I'm putting pi over 3, and it's going to go into the sine machine. I put that in. Now, I would get some value out of there, right? We could look that up on the unit circle. It's a 60-degree angle. What would it be? I believe pi over 3 over 2, if I'm thinking of that right. So that's what would come out. Now, it's instantly going to roll right into the inverse machine. Now, if you think this through here, I could look up that value on the unit circle. It'd be fine. But on this case, I don't even need to. What goes into the machine, I have now the inverse on the other side. So I'm going to get right back to where I started, right? You see that? These are opposites of each other. They undo each other. So pi over 3 went in. And what came out the other side was pi over 3. Now here's where things get a little tricky. Don't forget, we have our restrictions on the domain, or the range of a sine and inverse sine function. It has to be between negative pi over 2 and pi over 2. Okay, well this worked. This was perfectly fine. Pi over 3 is inside of this. So if I create this assembly line, what we're going to get out is pi over 3. The angle went in, it gets signed. It gets unsigned, we get right back to where we started. Okay, does that make sense? Now, that's not going to work as well on this one. So we create the machine, and 2 pi over 3 goes into the sine function. Okay? Now here's the problem. We're coming in, if we instantly roll right into the inverse sine function, what we would get is right back to 2 pi over 3, but 2 pi over 3 is not an acceptable value. So it's outside. So we could do this several ways. We could then try to adjust this. We could do what we did in the last one, and we could say, okay, let's just take away one trip around the circle. We're too big, so we could subtract away 2 pi. That would work. That would be an acceptable way of doing it. But for the large majority of these problems, let me give you another way that I think is going to be simpler. So what I'm saying is, this one's not going to just get us right back to where we started. because 2 pi over 3 is not acceptable to inverse sine. So what I'm going to do here is I'm just going to work this. With a unit circle, this is not hard. If I just do this, I'm going to find sine of 2 pi over 3 is going to be, that's 60, and the second quadrant is going to be radical 3 over 2. Now, here's all I'm going to do. I'm just going to say, okay, when is the inverse sine allowed to be radical 3 over 2? But it has to be in that acceptable range. Well, inverse sine of radical 3 over 2, which is what we practiced in the last video, that's going to be pi over 3. That's inside of the acceptable range. So I would do this off my unit circle is what I'm saying. Look up sine of 2 pi over 3, and you're going to get pi over 3. Just read that off my unit circle. Now, I want to do the inverse and get back to an angle, but I need an angle in this range that has a value of radical 3 over 2. That's pi over 3. Give me just a second here. I got to pause this. All right, sorry about that. So here's what I was doing. I was doing this one, and what we said is we just look up on the unit circle the value of that sine takes at 2 pi over 3. We're going to get radical 3 over 2. Now all I have to do is say, okay, what angle has a sine value of radical 3 over 2, but it's got to be within that acceptable range of this. Now, if you look at your unit circle and you're saying, okay, what angle has a value of radical 3 over 2, you're now going to limit it to quadrants 1 and quadrants 4. And if you look in those two quadrants, you're going to get a value of radical 3 over 2 at pi over 3. Now, let's try it again here. So these are opposites of each other. So if we undo each other, we would just get 2 pi over 3. Well, is that acceptable? Because remember, we had an inverse in here. So is that okay? Well, yeah, this one is. Yeah, I had to make sure. Yeah. Okay, so inverse cosine needs to be between 0 and pi. Well, we are. So this one's okay, and we're done. Hold on. Let's just do it right here. Okay. So this one's fine. Now, how about this? Okay, well, if we undo each other right here, we would get negative pi over 3. That's not in the acceptable range. So let's just work this, just using our unit circle. We're going to read it off of there. This is a 60-degree reference angle, and it's in quadrant 4. So you can just read this. I'm just doing this from my head. But so in quadrant 4, a value of cosine is 1/2. Also, positive or negative? Yeah, positive 1/2. So the value of this inside is 1/2. Okay, well, let's do what we did before in the last section. What angle has a cosine of 1/2, but it's between 0 and pi? When does that occur? Well, that occurs at positive pi over 3. And so I'm done. Okay, let's try a couple more. Now these, I'd recommend follow me here and don't try this on your own because this gets a little tricky here. So tangent, we saw, has to go between negative pi over 2 and pi over 2. Okay, so this is what we're going to do. Now, these undo each other, and pi over 8's fine. So we're done. There's nothing else to do. We're already finished because it's in the acceptable range. Now, let's do this again here. Now, I don't like this one because this is going to have to take a little different approach. But if we undo these from each other, we would have 11 pi over 9. That's too big. This would be, so quadrant 1 and 4 is what tangent can accept. Do you see what I mean here? But this is going to be in quadrant 3. This is more than a half a trip around. This is going to be quadrant 3. So that's not going to work. And what's strange about this one is that we can't look this up. I don't have these values on my unit circle, so we're going to have to try a little different approach. So I know if these undo each other, I'd get 11 pi over 9. But that's not in the acceptable region, and so I'm going to do like we did in the previous video. I'm going to just take off one period of tangent. I'm going to take off 9 pi over 9. I'm too big. This is too big. So I'm going to take off one trip around, and then I would have 2 pi over 9, which is in the acceptable region. So a different approach there. I like the other approach better. But so again, let me talk you through these. These undo each other, and it's in the acceptable region, so we're fine. Now this one doesn't. If you undo these, you get 11 pi over 9, which is not acceptable. So what I was recommending before for sine and cosine, you just read it off the chart. You would have found the value of this, and then you would find the angle off the chart that has that same value, but is in the acceptable region. We can't do that here. So let's just pretend these undid each other. We get 11 pi over 9, but that isn't going to work. It's not in the region. So what I'm going to do is I'm going to subtract one period of tangent, because if you subtract pi, you always get the same value. So I did. I subtracted one value of pi, because you'll always get the same value. I got 2 pi over 9. That is in the acceptable region, so I'm good. Okay, now there's a lot in this. I don't think it's terribly hard, but it's a lot of ideas. So now we're going to talk about the composites that go the other way around. So what we've seen so far is, oh no, hold on. No, their notation is wrong. That's not right. Okay, hold on, I'm getting confused here. No, we're still doing the same thing. We've got another approach. I don't know if that's coming in this. So far we're doing the same thing. We've still got the inverse on the outside. Now they showed a method here that's in the book that I don't think is a particularly good idea here. So I'm going to avoid it. But what they were doing here in these last couple slides that I skipped over pretty quickly, they were just remembering the idea, what's the technical term, that they're co-function relationship. Do you remember that? I don't even know if I want to explain this here, but I guess I'll just say it real quickly. Do you remember that if you had the sine of 30 in a triangle, it would be the same as the cosine of 60? We mentioned that in an earlier video, and the logic just proves that that has to be the case. Now I'm not going to go through all that again because I'm skipping the idea, but so they're trying to say that if these are co-functions, cosine and sine, so you could use that co-function relationship to solve this problem. And it's clever and it's a good idea, but I think it's a little more than is necessary. So let's do this just the way we've been doing it. What I'm going to do here is, these are not opposites. They're not going to undo each other here. So I've got to do the approach that we were doing that I was showing you before. I'm going to just look up the value of cosine of 13 pi over 6. Now, can I use what they did? Yeah, that's too big, right? So if you were looking on your unit circle, do you see we're going to take the coterminal angle, and what it would be is the same thing as pi over 6. This is all the way around the circle and a little bit more. So I'm going to use pi over 6 instead. Now I would look that up on my unit circle. If you don't have it memorized, it'd be radical 3 over 2. That's the value. Now all we're going to do now is say, okay, when does the inverse sine have a value of radical 3 over 2 within sine's acceptable region? Quadrants 4 through quadrant 1. Okay, well if I look that up, it has an acceptable value at pi over 3. I'm just reading that off my chart. Sine has an acceptable value, has the angle that makes radical 3 over 2 for sine that's in that acceptable region is pi over 3. Just reading it right off my unit circle. Okay, now they're doing the coterminal partnership thing. I don't think it's worth the confusion there, so we're going to skip that. Okay, now let's play this game again. We're going to just evaluate this off of our unit circle. Now this is not on my unit circle. It's going the wrong way, so we don't have those. And it's actually gone all the way around and plus some. So what we're going to do is we're just going to do the coterminal angle here. So do you see 8 pi over 4 would be one trip around. Now I'm at negative 3 pi over 4. Now you're probably okay understanding what that would be at this point, but let's just go ahead and make it positive, and we're going to spin around one more time. Okay, so we're looking for, this is the exact same thing as finding the sine of 5 pi over 4. Okay, if I look that up, this is in quadrant 3. If I look that up, I'm going to get negative radical 2 over 2. So I need the inverse cosine now of negative radical 2 over 2, but I need it to be between 0 and pi. That's our restriction. It has to be in that region. Okay, so if I look at my unit circle, when is that going to be negative between there? It's going to be negative at 3 pi over 4. Does that make sense? Okay, now this is what I thought was coming. There's a lot of ideas here. I'm sorry, this is going to be a long video. This is what I was talking about before. Now we're going to go the other way around. Okay, so what we had before is that the inverse was on the outside. But now what we're going to do is we're going to put the inverse on the inside. And the way we solve this is different. So let's take a look. We're going to use the Pythagorean theorem. Okay, now watch the logic here. If I have an inverse function, what it means is there's some angle that has a value, a cosine ratio of 4 over 5. Okay, now I could go ahead and try to work it like this, but what the proper way is to think of this. I'm going to create a triangle here. Now I have 4 over 5. Okay, so cosine is adjacent over hypotenuse. Do you agree with that? So I'm now going to use the Pythagorean theorem to find this missing side. I'm going to complete this triangle. And I know this one because it's a special triangle, but it's going to turn out to be 3. But what I would do is a squared plus b squared equals c squared. I'm just going to call that side x squared plus 4 squared equals 5 squared. So when I solve this, I'm going to get down to x squared is 9. So this is 16, that's 25. X squared is 9, so x has to be 3. All right. Well, I know all the sides of the triangle. Well, what's the sine then? This is the triangle that this angle must build. Well, what's the value of the sine? It's opposite over hypotenuse. It must be 3 over 5. Now they're working in a different way, but it's got to be 3 over 5. Yeah, hold on, I'm thinking about. Yeah, I'm trying to follow through their logic here on the way they're doing it. It's possible that you could get plus or minus 3 over 5. I know that this triangle, because this was positive, my x went this direction. I'm trying to think why they're assuming that's in quadrant 1. Hold on, I got to think about that. Let me keep going here to see if we run into that trouble again. Okay, so I am going to do the same thing. I'm going to build a triangle out of this value here. So let's build one. Remember, tangent is sine over cosine, or opposite over hypotenuse. So here's what I know. I know that the opposite is 5, the adjacent is 12, and I don't know the hypotenuse. Now this turns out to be a special one again, but let's just work it. We'd have 5 squared plus 12 squared equals x squared. Now when I crunch this down, what you're going to get is x is 13. Okay? So I now know this is 13. I've got a complete triangle. Let's just find the cosine of this angle in this triangle that this built. Well, cosine is adjacent over hypotenuse. So the value would be 12 over 13. So one more time, here's what I'm doing. I'm going to use, this is different because the inverse is on the inside. And what I'm going to do instead of trying to find all the values, is I'm just going to build a triangle based off this angle. There's some angle that has this tangent of 5 over 12, so I'm going to build it in a triangle. So opposite over adjacent would be 5 over 12. If I have two sides of a right triangle, I can always find the third. If I have a complete triangle, I can then find the cosine simply by its definition. It's adjacent over the hypotenuse. Okay, so there's a lot here. I hope that makes some sense. If you, there's so much. I guess what I would say if I were trying to wrap this up is just make sure you understand that the machines are different. Let me go back a slide. I want to go to here. Just make sure you understand the machines are quite different. If you do this, if you're starting with this, you're just going to read the values off the unit circle. It's all a unit circle exercise. You're going to just look up the value of the inside, and then you're going to go and find the angle that makes that happen, but you're keeping in mind the restriction. If you have this type of problem, what you're going to do is build. You're going to just go ahead and build the triangle off of these values. You can build a triangle that has the values that are indicated here. Finish that triangle by the Pythagorean theorem, and then you can just read the value of sine, cosine, or tangent off the triangle that you've just created.